In this video, we'll study inequalities in basic probability theory. Now, we already know that probability of any event, PA, it is defined as number of elements in set A upon number of elements in sample space, and we know that any probability will always lie between 0 and 1, and that is the first and most basic inequality relationship in probability. So any probability must always lie between 0 and 1. Now, when we have two events, A and B, then we can always draw them on Venn diagram. Now, suppose this is A, this is B, and that's your sample space. Now, if we look at this region, A intersection B, we know that number of elements in A intersection B will always be less than or equal to. Now, this probability will always be less than A and will always be less than B. So, it will always be less than minimum of whichever is smaller, either NA or NB, and subsequently we can write probability of A intersection B will be less than or equal to minimum of probability of A and probability of B. Then the same way, if we look at A union B, now A union B is this entire region. Now we know that N A union B will always be greater than or equal to. Now it is greater than both A and it is greater than B. So it will be greater than whichever is greater of these two. Maximum of NA and NB, or we can write probability of A union B will always be greater than or equal to maximum of probability of A and probability of B. Now, there will be some questions where we'll be given PA and PB, and then we'll be asked to find minimum or maximum value of A union B and A intersection B. Now, we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. Now, we know that probability of A union B, it is always greater than or equal to maximum of probability of A and probability of B, and it will always be less than or equal to PA plus PB. In the same way, we can write this condition for P intersection B. So we can write PA intersection B. It will be PA plus PB minus PA union B. Now we know that probability of A intersection B, it will always be less than or equal to minimum of PA and PB, and we know that maximum value of this probability A union B is 1, so it will always be greater than this PA plus PB minus 1. Now, if one event is subset of another, say for example, we have two events, A and B is contained in A, then number of elements in B is always less than or equal to number of elements in A. So basically, probability of B will always be less than or equal to probability of A. Then there can be inequality relationships in conditional probability also. Say for example, probability of A by B. Now we know that probability of A by B is probability of A intersection B upon probability of B. Now we know that in this case, probability of B, it must be greater than 0 but less than or equal to 1. Now if we divide A intersection B with any number whose value lies between 0 and 1 including 1, that means it will always be greater than or equal to probability of A intersection B. Now we can also define probability relationships in multiple events. Say for example, in case of 3 events. Suppose we have 3 events A, B and C. So we have 3 events A, B and C. Now this probability, which is probability of A intersection B intersection C, will always be less than or equal to minimum of probability of A intersection B, probability of B intersection C, and probability of C intersection A, and which is less than minimum of probability of A, probability of B, and probability of C. And in the same way, we can define probability of A union B union C, and it will always be greater than or equal to maximum of P intersection B, P B intersection C, P C intersection A. It is also greater than or equal to maximum of PA, PB, and PC, and this is clearly greater than maximum of this value. So there are many kinds of inequalities possible in basic probability theory. Now let us take up some questions. Now here the question is, for two events A and B, probability of A is 3 by 5 and probability of B is 2 by 3, then which of the following is or are correct? Now we know that P A union B will be greater than or equal to maximum of P and PB, because it is a superset, which in this case is 2 by 3. That means probability of A union B will always be greater than or equal to 2 by 3. Now we also know that any probability is always less than or equal to 1. So this value will always lie between 2 by 3 and 1. Now if we look at probability of A intersection B, it will be PA plus PB minus PA union B. Now if we look at PA plus PB, it will be 9 plus 10, 19 by 15 minus PA union B. Now we'll get this minimum value when PA union B is maximum and maximum value of PA union B is 1. So 19 by 15 minus 1 will be simply 4 by 15. So PA union B minimum value will be 4 by 15, and we'll get its maximum value when A union B is minimum, which is 2 by 3. So 19 by 15 minus 2 by 3 will be simply 9 by 15, which is 3 by 5. So that means this option C is also correct. Now we look at probability of A intersection B naught. Now probability of A intersection B naught is probability of A minus probability of A intersection B. Now probability of A is 3 by 5 minus probability of A intersection B. Now we are looking for its maximum value. Its value will be maximum when value of A intersection B is minimum. So P A intersection B naught will always be less than or equal to 3 by 5 minus 4 by 15, which is 5 by 15, that is 1 by 3. That means this option A is also correct. Now if we look at this option D is probability of A naught upon B. Now probability of A naught upon B is probability of A naught intersection B upon probability of B, or it will be this probability of B minus probability of A intersection B upon probability of B. So it will be 1 minus, now P intersection B will work out, and probability of B is 2 by 3. So it will be this 3 by 2 into probability of A intersection B. Now if we look at its maximum value, in that case we have to look for minimum value of A intersection B, and minimum value of A intersection B is 4 by 15. So it will be into 4 by 15, so which is 2 by 5. So it will be 3 by 5. So its maximum value is 3 by 5, And for minimum, we'll put this as 3 by 5. So there'll be 9 by 10 and 1 minus 9 by 10 is 1 by 10. So its minimum value will be 1 by 10. That means this option D is also correct. So all the 4 options are correct for this question. Now here the question is, let E, F and G be 3 events having probabilities 1 by 8, 1 by 6 and 1 by 4 and their intersection is 1 by 10. Then which of the following is correct? So we have 3 events E, F and G. So this is E, F and G. So let this be E, this is F and let this be G. Now it is given that probability of E is 1 by 8, probability of F is 1 by 6 and probability of G is 1 by 4 and their intersection it is given as 1 by 10. Then which of the following is correct? Now we know that probability of E intersection F will be less than or equal to minimum of probability of E and F, and in between E and F the smaller value is 1 by 8, so it will be always less than 1 by 8. In the same way, probability of F intersection G will be less than smaller value between F and G, which is 1 by 6, and the same way probability of E intersection G will be less than or equal to 1 by 8. Now if we look at probability of E union F union G, we know that this probability will always be less than probability of E plus probability of F plus probability of G. Now probability of E is 1 by 8, F is 1 by 6 and this is 1 by 4. Now this is 24, 3, 4 and 6. So it will be simply 13 by 24. So this probability of E union F union G, it is less than or equal to 13 by 24 and that's your option C. Now if we look at this probability, which is probability of E intersection F intersection G naught. Now probability of E intersection F intersection G naught is actually this probability. This probability is equal to probability of E intersection F minus probability of E intersection F intersection G. Now this is probability of E intersection F minus, and this probability it is 1 by 10. Now we know that probability of E intersection F, it is always less than or equal to 1 by 8. So its maximum value is 1 by 8. So it will always be less than or equal to 1 by 8 minus 1 by 10, which is 1 by 40. That means this option A is also correct. Now we look at this option B. Then option B is probability of E complement intersection F intersection G. Now it will again be probability of F intersection G minus probability of E intersection F intersection G. Now maximum value of F intersection G is 1 by 6. So it will always be less than or equal to 1 by 6 minus, and this intersection is 1 by 10. So it will be 4 by 60, which is 1 by 50. So that means this option B is also correct. Now if we look at this probability, which is E naught intersection F naught intersection G naught. So it will be this region, and this probability will be given by 1 minus probability of E union G union F. Now this probability will be minimum when this value is maximum. So it will always be greater than or equal to 1 minus 13 by 24, which is 11 by 24. So that means this option D is incorrect. Now the question is, probability of A is 1 by 2 and probability of B is 2 by 3. Now we know that P A union B is always greater than or equal to maximum of PA and PB. Now maximum of P and PB is PB. That means probability of A union B, it must be greater than or equal to 2 by 3. And we know that any probability is always less than or equal to 1. That means this option A, it is correct. Now if we look at A intersection B, we can write probability of A intersection B as probability of A plus probability of B minus probability of A union B, which is 7 by 6 minus probability of A union B. Now this value will be maximum when A union B is minimum, which is 2 by 3. So 7 by 6 minus 2 by 3, and there will be 7 minus 4, which is 1 by 2. So its maximum value will be 1 by 2 and will be minimum when we put maximum value of A union B, which is 1, which is 1 by 6. So this value will lie between 1 by 6 and 1 by 2. So that means option C is also correct. Now we look at this option B. This is probability of A intersection B naught, and it is probability of A minus probability of A intersection B. Now probability of A is 1 by 2 minus probability of A intersection B. Now it will have its maximum value when A intersection B is minimum. Its minimum value is 1 by 6. So if we put 1 by 2 minus 1 by 6, it will be 3 minus 1 by 6. So it will be simply 1 by 3. That means this option B is also correct. Now the same way we can write probability of A naught intersection B. Now probability of A naught intersection B, it is probability of B minus probability of A intersection B. Now probability of B is 2 by 3 minus A intersection B has two values, 1 by 6 and 1 by 2. Now we take 1 by 6, then it will be 1 by 2, which is its maximum value, and if we put 1 by 2, then it will be this 1 by 6. So that means all the four options A, B, C, D, they are correct. Now the question is, a number A is randomly selected from the set from 0 to 99. The number B is selected from the same set. The probability that number 3 to the power A plus 7 to the power B has a digit equal to 8 at its unit place. Now if we look at powers of 3, 3 to the power 0 is 1, 3 to the power 1 has 3 in the units place, 3 square has 9, 3 cube has 27, and 3 to the power 4 is 1. So these values, they are going to repeat after every 4 powers. Then the same way we look at powers of 7. 7 to the power 0 is 1. 7 to the power 1 is 7. 7 square has 9 in the units place. 7 cube has 3. And 7 to the power 4 has 1. Again, we'll have these values repeated after every 4 power. Now it says we need to find the probability that the number has digit equal to 8 in the units place. Now we'll get 8 in the units place if we choose 1 here, and then correspondingly we have 7 here. If we choose 9 here and we take 9 from this, or if we choose 7 from this and we choose 1 from this. Now if we look at values of A, then out of these 100, we have 25 sets of 1, 3, 9 and 7 each. So probability of choosing this favorable A will be simply 3 divided by 4. And once we have chosen A, then B is automatically chosen 1 out of 4. So it will be this 1 by 4. So the required probability is 3 by 16, and that's your option D. Now the question is, for any two events A and B, which of the following is true? Now the first one is P A by B. Now we know that P A by B is P A intersection B upon probability of B. We are given that probability of B is unequal to 0. Now we can write probability of A intersection B as probability of A plus probability of B minus probability of A union B upon probability of B. Now maximum value of A union B is 1. So it will always be greater than or equal to probability of A plus probability of B minus 1 upon probability of B. That means this option A, it is correct. Now if we look at this option B, it is probability of A intersection B naught. Now probability of A intersection B naught, it is clearly probability of A minus probability of A intersection B, because it is that part of A which doesn't contain B. So there will be probability of A minus probability of A intersection B. So option B is also correct. Now if A and B are independent, then we can write probability of A union B as 1 minus probability of A union B complement, and this is 1 minus probability of A complement intersection B complement, and we can write this as 1 minus probability of A complement into probability of B complement. That means option C is also correct. Now what about option D? If A and B are disjoint, then we can write probability of A union B as probability of A plus probability of B minus probability of A intersection B, which in this case will be 0. So it will be simply this PA plus PB, and we cannot write it in this form. So the correct options are A, B and C. Now here the question is, if A and B are independent events, then prove that probability of A union B into probability of A naught intersection B naught, it is always less than or equal to probability of C, where C is an event defined that exactly one of A or B occurs. Now first we will define this probability of C. Now probability of C is exactly one of A or B occurs. So it will be this probability of A intersection B naught plus probability of A naught intersection B. Now this is probability of A into probability of B naught plus probability of A naught into probability of B. Now if we look at this left hand side, we can write this left hand side as probability of A union B into probability of A naught intersection B naught. Now we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. So this probability of A union B will always be less than or equal to probability of A plus probability of B. So we can write this probability of A union B will be less than or equal to PA plus PB, and here since A and B they are independent, we can write this as probability of A naught into probability of B naught. Now it will be this PA into PA naught into PB naught plus PB into PA naught into PB naught. Now clearly PA naught and PB naught, they are less than or equal to 1, and if they are less than or equal to 1, that means this is less than or equal to PA into PB naught plus PB into PA naught, which is nothing but PC. So we have proved that probability of A union B into probability of A naught intersection B naught will always be less than or equal to probability of C if A and B are independent and C is an event defined that exactly one of A or B occurs. Now here the question is, consider a function fx equals x cube plus ax square plus bx plus c, where a, b, c are chosen by throwing a die 3 times. Now find the probability that fx is an increasing function. Now you find total number of ways of choosing a, b, c. Now for each of a, b and c we have 6 options. So total will be 6 into 6 into 6, that is 216 times. Now this function has to be an increasing function. Now it will be increasing if f dash x, which is 3x square plus 2ax plus b, it is greater than or equal to 0. Now this is always positive for all x when leading coefficient is positive and when discriminant is less than or equal to 0. So the condition that we have here is 4a square minus 12b should be less than or equal to 0, or when a square is less than or equal to 3b. Now we need to choose the values of a and b. Now if we take b as 1, then value of a can be 1. Now if we take b as 2, it will be 6. Now we can take the value 1 and 2. If b is 3, then a can take the value 1, 2 and 3. If B is 4, again it will be 1, 2, 3. If B is 5, again we'll have 1, 2, 3. And if B is 6, value of A will be 1, 2, 3 and 4. So altogether we have these 16 cases, and in each case we can have 6 different values of C. So it will be 16 into 6. So this required probability will be 16 into 6 divided by 216. Now this is 36, which is 4 by 9, and that's your option C.